want to go ahead and introduce our first speaker of our last session today, Greg Kingsley. And I think, Greg, I see you online there. Greg is the president and CEO of KL&A Engineers and Builders in Golden, Colorado, a firm of 95 that includes structural engineers, detailers, and construction managers. He enjoys working on innovative wood structures of all kinds, especially in mass timber. Greg is arguably one of the most innovative and experienced engineers in this realm and always impresses us with his abilities and projects. And Greg, buddy, I know every time I've seen you present multiple times, and every time I always learn something new from you. So no pressure. I feel like I'm going to learn so much more again this time. So we're absolutely thrilled to have you with us and appreciate your time. So it's all yours, sir.
All right. Thank you very much, Bruce. Really appreciate it. Can you see my screen? I can't tell from there. It's all good?
Yeah, you're good, Greg. Go ahead.
Good. So I'm going to talk a little bit about some of the same things that the other speakers have talked about, but from the perspective of engineers and architects from the very earliest part of the project, from the very first decisions that you set out to make. And I'll reiterate up front what you've heard from others, I think, in all three presentations, that hopefully, even at the very earliest moment, hopefully you're making those decisions in a collaborative way with your other design and trade partners on the project. So here's the outline, how I'm going to go about doing that. First, we're going to talk about what drives the cost of some of the components of mass timber construction, the mass timber panels, and then beams and columns. And then we're going to wrap that into a base study or two that shows the effect of those costs on different grid choices. Then we'll get into mass timber connections just a little bit, and then we'll fold steel beams and columns into the mix for a hybrid study. And if I have time at the end, I'll spend a couple minutes looking at an entire building system and what they cost. So starting from the very beginning, let's look at mass timber panels and what they cost. You already heard Anthony describe to you some of the different kinds, parts and pieces that you can use. You'll hear me talking almost exclusively about CLT, but I'm pretty sure most of the conclusions that I'm drawing can really be applied to all these other systems. So please don't take it as limiting to just CLT. The next image, you've seen another version of this, a little bit later one that I think Chris showed, starting from around here and moving forward. This is the commodity price for lumber. And I just really showed this slide to emphasize primarily it's a little bit of self-protection so that you realize that costs will change as a result of the changes in commodity prices, which can be pretty dramatic. So that means that the cost per square foot that you're going to see later on are really from a snapshot in time from somewhere around in here, and they may or may not apply right now. So managing that risk was a part of what Chris talked to you about at some length. Another thing that affects cost is supply. I think this is good news that the supply in the US is growing pretty rapidly. The light colored green bars indicate the manufacturing capacity for building CLT, building grade CLT, and it's growing pretty quickly. In fact, so quickly, I used to show a list of manufacturers here, and I can no longer keep up with all the changes of who's been certified and not. So I'll leave that to WoodWorks to advise you on who those folks are. But whoever they are, I will tell you that your choice of the supplier will affect the cost of your system, because each one, as you get to know them, has their own panel widths, their own efficient panel lengths, different lamination thicknesses. They use E-rated and V-rated materials, different species, different finishes. All those will have an effect on cost. So that early engagement of the fabricator to understand what they can supply specifically and how their product affects your choices, really important. Another key and huge takeaway, if you take away one key thing from this, it's that the CLT cost or mass timber cost in general depends on wood volume. It really is the driving factors, the amount of wood fiber in the product. I like this slide. It just illustrates 3, 5, 7, and 9 ply CLT. And I'll tell you that in my designs, I try to stick in this realm of 3 and 5 ply for the most part, and we step into 7 ply every now and then. If I get down into 9 ply, my advice is to just start over, unless it's a very small area of your building, because that's a lot of volume of wood and it's going to cost a lot of money. So looking at trying to develop a model that included CLT costs, I looked at a bunch of different manufacturers. This slide shows CLT panel thickness for different span lengths for 4 randomly selected manufacturers. And you can see there's quite a spread in there. And I did not want to pin my study to any individual manufacturer. So I invented my own, which I called Dr. K's generic CLT. So in the prices and volume studies that you see going forward, this is this made up manufacturer. Taking that a step further, Dr. K's CLT depends and costs not only on the volume, which is pretty much driven by the thickness, 3, 5, 7, and 9 ply, but also by the panel length. And you heard Justin talk about this a little bit, optimizing design to eliminate waste in terms of panels. At Dr. K's, we make a 40-foot panel, and that there's different efficiencies at different lengths that affect the cost of the panel. And I'll point out that in this sort of hypothetical scenario, there's an added expense for a 25-foot CLT panel. That'll pop up later. This is based on real costs from a real manufacturer, but sort of adjusted hypothetically for my study. So that is the CLT panel cost. Let's look at glue lambs. That's the columns and beams and girders that go into your system. And really only have one key slide here, which illustrates a really interesting point for me, which is that the unit cost of glue lamb, which is the cost per volume over here, depends on the width of the beam or column, right? So I illustrate that by showing in a project of ours where we used double girders, that theoretically, if we just think about material cost, you know, and don't think about erecting number of pieces and so on, just material cost, that the cost of those 2 girders is less than the cost of the same amount of wood if it had been ordered as a single girder. I think that's a really interesting point, and it certainly helped us drive us towards a solution here, which also was helpful later on in terms of connections, which we'll discuss later. So as I said, we're going to fold those into some base studies, all those material things. So I tried to include in my base study the CLT cost, as I discussed, and then the cost of wood beams and girders and the columns. Also got into connections, which I'll discuss in detail a little bit later, as I will the steel beams, girders, and columns for a hybrid system. I do include concrete non-combustible topping for my study, and it's the same for everything really, so it didn't really vary from one study to the next, or one grid to the next. I'll emphasize one more time that these are conceptual cost estimates, and I think they're pretty interesting for comparing different grids in different systems, as we're going to do, but not accurate enough to compare to steel versus concrete, so please don't use these numbers to do that. So here's the first one. We'll spend a minute on this slide because it's kind of juicy, a lot of information here. The first grid study I did, I used what Anthony called a post beam plate system, where there's a post and a beam, but there's no interior beams, just CLT spanning between these framed bents, okay? So the way I set up this study was to start with a 20-foot span for the bent, and then I put the 2 bents just 10 feet apart, okay? That's the first study, that's the 10. Then I started pulling them further apart in 2-foot increments to 12, 14, 16, and so on until they were 30 feet apart. I looked at the total cost of that system, and that's what's represented on the left axis here. Each bar represents the cost per square foot. The brown section shows the cost of the wood. The red section shows the cost of the connections, the wood connections, and the gray section, the cost of the non-combustible topping, which you'll see is the same for all of them, okay? One other thing shown on this graph is the yellow line. That relates to the right-hand side. That's the clear height to the bottom of the girder over here, assuming a 12-foot floor-to-floor height, just picked arbitrarily. I just wanted to show that really everything that my architectural clients were interested in, which is column density cost, and head height in one picture. You'll see something interesting here as the head height bumps up. That shows where at a certain point I started getting down to an 8.5 foot clear height. A little architect in my head said that was a bad idea, so I doubled up the girders to decrease the depth, and that's what you see there. It's also kind of represented in the cost. The big conclusion you see here, you can kind of watch as we move from 3-ply CLT to 5-ply CLT to 7-ply, and then on up to 9-ply. And you also see, remember that little bump around 25 feet that I showed in terms of the cost of the CLT panels? You can see that little bump up here in that cost. In general, with this system, basically the longer the span of the CLT, the more expensive it gets. So normally what we see here is you pick a CLT thickness that's required to get the fire rating you need, and then optimize the span to maximize the utility of that CLT. So let's look at another study. This one is a square bay. This one has columns, and girders, but also has some filler beams or purlins in between, and the CLT spans between the beams. Now in this system, I started with a 16 by 16 grid and just started pulling the columns apart 2 feet increments, 18 by 18, 20 by 20, and on up to 36 square, right? And what's interesting here is that I kept the CLT thickness, in this case, constant at 3-ply. And in doing that, I kind of kept the cost of the wood system kind of consistent, right? Within a couple of bucks a square foot per system. But what changed was the cost per square foot of the connections. The more connections I have per square foot, the more it costs. And we'll get into that a little bit later. Ceiling height looks pretty good at this one. Actually did pretty good for the longer spans if you can accept 8 3/4 foot ceiling height. So moving on to the next study, I was interested in the aspect ratio of the overall grid system. When I look at a steel system, generally we believe that or know that a short girder with long beams is generally the most economical system for a rectangular grid. And I wondered if that was true for mass timber as well. So I went through this study and I started with a 15 by 15 grid, and then I added, I basically stretched the beams out 5 feet at a time until I got to 30 feet. Then I went back and added 5 feet to the girder and did it again down these rows. And I did another graph of those studies. So this graph shows some interesting stuff, okay? I start with this 15 by 15 grid. I end with 30 by 30. You can see this kind of sawtooth shape as I go up. As the beams get longer, the system gets more expensive, okay? And then I move to another girder height and I sawtooth again. These guys are a little bit higher because they're in that special zone of the 25-foot CLT in my pricing. And then up here, I have another sawtooth. Basically, the longer the beams get, the more expensive it gets. And to answer my aspect ratio question, I look, for example, at a 15-foot girder with a 30-foot beam. I get about 32 bucks a square foot. And I invert that. I look at a 30-foot girder with a 15-foot beam. I'm down at about 30 bucks a square foot. So now it looks like the rule of thumb that I have for steel structures is inverted for timber, at least based on this study. So I think that was an interesting point. So let's quick look at some pretty pictures instead of graphs. Here's a mass timber project that we did in Boulder. It's 2-story type 4 building. And here we chose to use that post beam plate system. The grid is 25 by 30. The span here is 30 feet. And then the span of the CLT is 25 feet. If you've been paying attention, you know that's a pretty long span and might be a particularly expensive one as well. We ended up really driving the design by owner requirements for openness in this area. It's a really beautiful building. It's a very successful building. But you'll see kind of a long span for the CLT. And you can actually see, at least in the previous slide, the thickness of that CLT, I think. is 7 ply at the floors and actually at the roofs as well. So we dipped into the larger sizes of CLT members. You'll also see how elegant and small those glulam girders might look compared to some other projects you've seen. That's because the architect was not ready to embrace the really deep girders that often come with really long spans. So they asked that we push the girder up so that the top of the girder met with the top of the CLT. That limited us then to single spans for the CLT, and then we had to DAP that into that system. So maybe not the most economical choices on this building. It was really driven by an architectural and owner-driven needs. But then we kind of went to school and learned some things. One thing that we really learned on this one and did right was to keep the connections simple, right? That's a good rule of thumb in terms of connection cost and how they affect your overall cost of your system. So getting into that, I think it's fair to say that the most economical connection systems for mass timber involve wood-to-wood bearing, where I'm dropping one piece onto another piece, and then simple connections driven by screws. I love this picture because it appears to show that that connection is so simple you don't even need to wear pants, and you don't need to think about safety or free edge protection. So apparently OSHA goes away as well. In order to quantify this for my model, what I did was to break connections down into 4 different classes. A simple class 1, which is just a bearing connection, like the one that you just saw. Another one step up, which is driven by bearing, but with some steel components, custom steel components included as well. And then I moved up into class 3, which is a proprietary connection, which is hidden. We've talked about these a little bit before, and these are actually pretty amazing products. They're completely hidden. They're elegant, they're constructible, and often are tested and fire rated as well. So they have really great things going for them, but they can get a little pricey. And especially if you get into the large class with lots of screws, that can make these guys add up pretty quickly. So in summary, our connection model is based on the connection material, the number of screws and bolts, the beam and girder end fabrication that's necessary, and the field installation costs. In general, the cost increases with our connection class, but most importantly, the cost increases with the reaction carried. If you want to walk away with a rule of thumb, the bigger the reaction, the more expensive the connection. So that's a good thing to pay attention to when you're starting to look at long span grid systems. So let's look at how that cost model affected a real project. This is Plat 15, recently completed project in Denver. It's a type 3B project on a 30 by 30 grid with 4 stories of CLT above a concrete podium that comes up to the above the first level. So that system is based on, as you can see, my 30 by 30 grid, and here the beams sit on top of the girders. We use that double girder system that I showed earlier on, which allowed the girder connections themselves to be bearing connections. And in so doing, in making that move, we ended up with a grid study just for this particular project, picking a 30 by 30 grid. The least expensive one here was the least expensive because of the savings in connection costs. The choices that we made saved us a couple, $2 to $3 a square foot on a 150,000 square foot building. That actually adds up. That meant a lot to our owner, and he was willing to pay the price. You can see here of a dropped ceiling height. This isn't that accurate, actually. It ended up being exactly 9 feet, or 9 feet 0 1/4. So this is what that system looked like in the end, right? You can see our dropped girder, dropped it about 16 inches below the bottom of the CLT so that we could sit the beams on top and make that connection simple. We also tried to make the connection of the girder to the column simple, also a bearing connection. The wood column actually continues all the way up through, but it's held back to make room for the girder connection here. There's a bearing plate that just fits around that internal column. You can see a couple of screws here, pretty hard to see, and there's a couple more up at the top. Very simple, fast to erect. Another kind of connection that's not so simple that I think is equally important is where we interface mass timber with other systems. I think that Chris brought this up. He actually had a category called adjacent structural systems. This is one of my obsessions because the concrete, in this case, the flat podium at plat 15, even when it's within spec, is plus or minus 3/4 of an inch, right? So we put some embeds in the top of the slab, and our drawing, that embed is perfectly at the top of the slab. In reality, we have to chisel away 3/4 of an inch to find where the embed was, and it's probably not so flat while it's in there. So we ended up actually custom cutting each of these HSS tubes, or cutting the bottom off to fit the location to be prepared for the arrival of the mass timber. We took another step and added another plate on top right here that goes on top of this plate to make sure that the bearing surface for the glulam column was dead level and in exactly the right place. And it really proved out so that when these columns showed up on the first day, interface between concrete and timber is often a place where work stops, where there's a delay, where you lose the advantage of speed of construction. And those guys went up in the morning without a hitch. Really kind of a proud moment for us. Looked at the same exact condition, but at a vertical interface. This is a concrete core. This is a connection that would ultimately be exposed. We needed to be able to design that connection to accommodate our plus or minus 3/4 of an inch. Actually, I think this one can handle an inch while still looking pretty. We had some little side plates on the side to hide the gaps. These again went up very quickly. We didn't have any interface issues where we ran into those different materials. So that's really key, because time is money, and that's what you're saving. And I want to emphasize, this is a designer issue. This is not a fabricator issue. This is what engineers need to be thinking about at the front end of the project. Another cost saver for us on this particular project was we got to use 50-foot panels from Nordic. They make long panels. That meant we covered a lot of area with each pick, and it meant that the structure went up pretty fast. I'm going to show you a quick time lapse. It shows the concrete going up. See, relatively slowly. You're going to see the timber show up after the top of the post-tension slab. Goes up 2 stories and stops right here because it's Christmas time. Everybody went home and took a break, came back after a couple, 3 weeks, and kept going. So I want to emphasize this is about 6 guys putting this timber up on their own. And if you watch this video enough times as I have, you'll see there's a lot fewer dumpsters, a lot less site congestion, and a whole lot fewer people on site during the mass timber construction. So speed is key. So we looked at, a little bit earlier at a hybrid system. I would just want to go in really quickly and talk about the cost of steel. Same commodity argument applies. Rule of thumb for steel, 2/3 of the cost is labor on site and handling, not material. So that makes it different than mass timber. I'll jump past this one. To get to a conclusion about that, we did the exact same base study that we did for wood with the hybrid system. In the hybrid system, we had steel columns, beams, girders, and CLT panels spanning between the beams. This is the graph you guys saw before, so you've seen that before. Here's the same one for a hybrid system. An interesting point. So the CLT stays dead constant until I get to that 25-foot zone based for my particular model. But the interesting thing to me is that this sawtooth shape is the opposite for steel than it is for wood. Steel loves long spans and fewer pieces, right? And it also means that when I did this study for this particular system, the optimum grid for the hybrid was either 20 by 30 or 30 by 30 in this case, where for the wood it had been 20 by 20 or 30 by 15. Conclusion from that, well, timber is not the same as steel. And if you try to mash the square peg into the round hole, putting a timber system on a steel or concrete grid, you probably won't get the most economical system. So I think I have about a minute or two left, just enough to show you really quickly a study that we did on a complete building system. We used the same kind of grid we had on Plat 15, and we went ahead and designed 3 buildings on that same grid, violating the rule that I just told you. But we did it in mass timber, steel, and concrete on kind of a grid that you might see for any one of them. And then we actually took it out to subcontractors, got costs based on the current market. Concrete building 1 and steel was about a 4.5% premium. And wow, mass timber was a 14% premium over the other 2. This is the place where mass timber often dies as lost in consideration of the project. But I think Justin pointed out that they did a similar study, and at the end of the day, the premium was mitigated by schedule. Had the same contractor that did Plat 15 look at this same study. And so we said, well, in fact, it takes 3 less months to erect this than the other 2. So if we include that in general conditions, it reduces the premium from 14 down to 7%. General requirements, equipment, waste management, now we're down to 2 3/8% or 0.38%. And then in a 4th pass, including urban site logistics for the Plat 15 site, we're down in the competitive zone. And if I cheat a little bit and include finishes, it gets even better. So the moral of this story is, if you want an accurate cost of what a mass timber system is, and time is money, you need to include the time in the estimate. So really quickly wrapping up, a couple of things I didn't address that I just want to let you know is all of the systems I looked at were unrated systems, and fire design can affect the wood volume, so that matters. And another thing that's been brought up is in terms of doing grid studies, you need to fold in MEP very early on. I love this solution at T3 in Minneapolis, where they put a short grid by the core, and that allowed them a shallow beam here that they could have a trunk line that could turn and run out in their beamless system to the exterior of the building. Quick conclusions: don't hammer square pegs into round holes. Timber is timber and steel is steel. Collaboration and coordination early is really critical. Engage fabricators early. And then after grids are set, don't forget other factors: connection costs, constructability, and interface with other materials. And I think I almost made it on time, Bruce.